Okay, this is the second installment of lecture 5 of the first lecture, sorry, of week 5 of CSC231, assembly language. And what we're going to do is look at more arithmetic instruction and understand a little better how to mix and match integers formatted as bytes, words, and double words, and discover something very interesting about Java as well, compiled languages in general, but Java in particular. So I'm planning on covering more instructions and to give you an idea of where the operations, the arithmetic instructions take place inside the Pentium. I have here the image of the die. The die is actually the silicon chip that is inside the processor. And here we see all the different components, and what is interesting for us is this part here with the word ALU on top, which I've added here, and ALU stands for Arithmetic and Logic Unit. So this block here contains thousands of transistors organized as if you will, a calculator, and that's where the additions and subtractions, multiplications will take place with the different registers. So it's a small part of the processor, but important, very important part as well. All right, so yes, very important warning here in terms of everything that we are doing. We are dealing with integers that are referred to as unsigned integers. These integers are only positive numbers from 0 to 4 billion something. We'll see later on how we can do arithmetic with negative numbers, and before that we'll have to take a look at how negative numbers are coded actually inside computers. So the first instruction that I want to look at is the INC instruction, and so that's the mnemonic for it. The way we will use it will be INC with an operand, only one operand, because we want to increment, so adding 1 to only one thing at a time. So it's unlike the add or the move that have two operands. INC has only one, and the operand can be a register, an 8-bit register, a 16-bit register, a 32-bit register, or memory as a byte, memory as a word, memory as a double word. So these are variables in memory. These are registers. Any of the data registers, general purpose registers, so that would be, for example, AL, could be BX, could be ECX for that. So here are examples. So here I have 3 variables, alpha, beta, and x. Alpha is a byte, see the dB here. Beta is a word, 16 bits, store the number 4 in there. And x is a double word of 32 bits, and it contains 0. So these are my 3 variables in my data section. I don't have the section.data and section.text to simplify the code here, but you would need that. And here are examples of increment instruction. Increment AL. Whatever is in the AL register would get incremented by 1. So if you remember, AL is the lowest byte of EAX. Increment CX. CX is the lowest word of ECX. It's 16 bits. Increment CX would add 1 to whatever is currently in CX. And increment EBX would add 1 to the contents of EBX as a 32-bit register. And if you want to increment some of these variables, for example, beta and x, you would say increment. And remember, we always want to add the size of the variable. And it's especially important with INC because NASM, if you remember, will look at these labels as addresses in memory of something, but it never remembers whether the something is a double word or a byte. So when it sees INC bracket beta, it has no idea if you mean the beta address that points to a byte or a word or a double word, so you have to tell it, and that's why we put it in front. So since beta contains 4, after the instruction I'm going to store 5 in beta. That's the result of this instruction. So you see I'm commenting with following the semicolon, I'm commenting what's happening here. And here increment d word x, because x is a dd, it's a double word. So increment double word x would add 1 to x, which started at 0, so I would end up putting 1 in x. So that's the result of that. Decrement, very similar. The mnemonic is dec. One operand only, because you just want to decrement only one thing. You can work with registers that are 8, 16, or 32 bits, and similarly with memory. Same example, so I think I can go quickly here. You will have figured out that I can decrement byte register or word register or double word register. Similarly, I can decrement the contents of a variable that is a word or a variable that is a double word. Okay. Multiply. Okay, so multiply is tricky. And with multiply, I'm going to multiply two operands together. However, when I'm going to write the multiply operation instruction, I will use only one operand. So it's kind of a strange instruction because it uses two operands, but I only write one, and the reason is that EAX or part of AX of EAX is going to always be by default one of the operands. So I can multiply a register, an 8-bit. All right, let me rephrase this. I can multiply 8-bit values in registers, or 16-bit values in registers, or 32-bit values in registers. Similarly, I can multiply information in memory that is as a byte, or as a 16-bit word, or as a 32-bit word. All right, before we look at MUL, I want to take a little sidestep and show you why MUL is different. And we've already done that in class once, but if you've missed it or forgotten it, let's review it. Assume that I have two binary numbers. So here I'm picking 4 bits because it's simpler to show what happens. If I'm multiplying the first number, which is 1001, by 1110, I'm getting 0 times 1 is 0, 0 times 0 is 0, 0 times 0 is 0, 0 times 1 is 0. I'm going to use the same rules that I'm using with decimal numbers. So this line corresponds to 0 times that. The next line corresponds to 1 times this, and I'm shifting to the left because this multiplier 1 is bigger than that by 1 base, so power of 2. So that's why I'm shifting to the left. So 1 times 1 is 1, 1 times 0 is 0, 1 times 0 is 0, 1 times 1 is 1. Then I'm multiplying this one with this. I'm getting that, shifted to the left. And finally, this one times that is this number. So you see that I have to shift to the left every result. And now I can add this together, and so when I add it together, I get this number, 0, 1, 1, 1, 1, 1, 1. And here I was lucky because there's no carry anywhere. So 0 plus 1 is 1, 0 plus 0 plus 1 is 1, there's no carry, 1, 1, 1. But I could imagine, for example, having a 1 here, and adding 1 plus 1 would generate a carry, this carry plus 1 would generate a carry, so it is possible that I could have another digit 1 at the front, in which case I would have 1, 2, 3, 4, 5, 6, 7, 8 digits, 8 bits. So in general, if you have 4 bits, when you multiply them by 4 other bits, or a number of 4 bits by a number of 4 bits, you're going to get 7 or 8 bits. So we're going to say that the result of multiplying a 4-bit number by another 4-bit number is an 8-bit number, because sometimes it's 8, sometimes it's 7, but we're going to keep the largest. And that is true for any number of bits. So if you multiply an 8-bit number by an 8-bit number, you're going to get a 16-bit number. And if you multiply your 32-bit number, which is what our registers are, by another 32-bit number, the result is going to be 64 bits. So that creates a challenge for the Intel designers. When they were designing the Pentium, they had to figure out how, because all the registers inside the Pentium are 32 bits, but your result is going to be 64, so you have to store that somewhere. So this is what they decided to do. They said, all right, if you want to multiply a 32-bit operand by something else, the something else has to be EAX. So one of the operands will be, if you're multiplying two 32-bit values together, you have to put one of them in EAX. You are forced to do so. So therefore, that's why the multiply instruction has only one operand, because the second one is EAX automatically. You have no choice. If your operand is 16 bits, then you're going to use the lower part of EAX, which is 16 bits, so it will be AX. And if you want to multiply an 8-bit value by another 8-bit value, then you put one of the 8-bit values in AL, then you can specify the operand, and that's the one you're going to see here. All right, so we'll do some examples of that right now. But it's important to realize that one of the two operands will be EAX, therefore you don't need to write comma EAX. It's implied. Okay, but now look at this. If this is 32 bits, which EAX is, and this is 32 bits, the result is 64. Then the Pentium will put that into two registers. So EDX will get the top 32 bits of the result, and EAX will get the bottom 32 bits of the result. Okay? If you multiply 32 bits by 32 bits, you get 64 bits. The lower 64 will go in EAX. The upper 64 will go in EDX. You have 64 bits. You have to store them in two registers. So the Pentium designers decided to do that. That was the rule they decided to adopt. If you're multiplying two 16-bit values together, one must be in AX, which is the 16-bit lower part of EAX. The other one can be whatever you want, wherever you want. And when you multiply these two together, you get a 32-bit value, and the lower part is going to go in AX, and the upper part in DX. That's the rule. You cannot change that. That's the way MUL is defined. I'm sure that you would suggest, well, why doesn't it go into EAX, which is 32? The answer is that at the time that, at some point, there were no EAX registers. The original, I think, 286, the registers were only 16 bits, so AX, there was nothing greater than 16. So AX plus operand will go into AX and DX. These were the only two registers available. Finally, if you multiply an AL, so it's an 8-bit value by another 8-bit value, one of the two has to go in AL by default. It's going to be implied. You multiply it by a second operand, and the result goes into AX. Okay. All right, so let's take a look at some example, and hopefully that will make sense. So again, I have a byte variable, I have a word variable, I have a double word variable, and I want to multiply alpha by here. So this instruction, mul byte alpha, will multiply whatever is in AL. So I better put something in AL first. I haven't shown it here. And AL will be multiplied by alpha, which is 3, and that's going to be put in AX. So now AX will contain 3 times, so 3 coming from alpha, 3 times whatever is in AL that I have put there beforehand. All right? And now here's an example of mul EBX. So if I see that EBX is a 32-bit register, so I know that automatically the mul is going to use EAX. That's the implied register. So whatever is in EAX is going to be multiplied by EBX, so that's what I have here. Whatever is in EAX and EBX are going to be multiplied together. 32 bits times 32 bits is going to be a 64-bit result. The lower part is going to go in EAX, the upper part in EDX. That's how I write it, EDX colon EAX. I'm specifying that this is a 64-bit value, and the lower part for you is EAX, the upper part is EDX. Okay, it's a little tricky, but it's also explained in the online resource. So now this has tremendous important consequences for us as programmers. Even if we don't program in assembly, these are the instructions that are available to the compiler. So when you write a program in Java, which is compiled, the compiler has to use the instructions from the Pentium to put together an executable. And the compiler knows about all these rules that I've just explained. So it knows that if you multiply two 32-bit numbers together, it has to use mul, and it knows that the lower part of the 64 bits are going to go in EAX and the upper part in EDX. but let's take a look at something here. So I'm going to illustrate something interesting. So I have a Java program called Java Limits, and I've already prepared it in the handout directory. You'll be able to get a copy of it if you want. I have my main program where I define a as an int, so that's an important detail. A is a 32-bit variable. Int for Java means 32-bit. I set it to 1, and then I'm creating a loop that's going to go 100 times. If int I equals 0 to 100, what I'm going to do is that I'm going to multiply a by itself. Sorry, I'm going to multiply a by 2 and store that back in a. So if a starts at 1 and I'm multiplying by 2, I'm going to get 2. 2 times 2, 4. 4 times 2, 8. 8 times 2, 16. So I'm going to see a growing 1, 2, 4, 8, all the powers of 2. And I'm printing each value here. A equals a. All right, let's take a look at that program. Okay, Java limit Java. So let's take a look at it. I have more. We're going to see something else very soon. But see, that part that we've just seen on the slide is here. Same code. So I'm going to run that. This code is inside a false condition, so it will never run. So it's like a comment. All right. So let's compile this quick. Redo my last Java C command. So I'm compiling Java limits, and now I'm going to run Java limits with the command Java. But I'm going to use a pipe. I'm going to show only one page of the output at a time so that I can take a look at it. So we'll see very soon that I can do that by piping. This little symbol here is a pipe. I'm taking the output of this, which will be 100 lines, but I'm showing them one page at a time with less. All right, not bad. So a equals 2, because a equals 1 is not shown. I'm only showing the result of the multiplication. So 1 times 2, 2, 4, 8, 16. So you see all this looks good. 1024, 2048, and so on. 65536. So you see that every time I have twice the previous line. So I'm going to go one line down. I'm going to keep on going. So see, I can see one line at a time. I'm using my arrow key on my keyboard. Oops, something interesting has just happened. So let's see, this is 1,000 million, from 1.0 billion to twice that, I'm getting a negative number. So we'll see a little later on why that happens. We have to be aware of that. That's because of the way negative numbers are coded in binary in a program. And so we have a first problem. So this is not the only problem, but the next problem, whoops, is that 2 times minus 2147483648 is 0, and 2 times 0 is 0. So my loop that keeps on going until 100 times, now my a variable has become 0. How could this happen? So I'm going to go till the very end. All right. So I type Q to quit out of this. All right, I'm back. Think about it. Why is that? Let's take a look again at my program. Maybe I can try to explain it here. Let's see Mac. Emacs that. Emacs. Java limits Java. No Windows. Alright, created a comment here. So when I start with a equals 1, the variable a is a lot of zeros. 1, 2, 3, 4, 5, 6, 7. Actually, instead of dealing with 32 bits, I'm going to use only 8. But the reasoning is exactly the same for 32. I'm just being lazy and I don't want to write 32 bits, but I'm going to play with 8. And the reasoning is exactly the same for 32. So let's assume, so that's the binary value of a at the very beginning. When I store 1 in a, 1 decimal is represented in binary like this. when I multiply a by 2, I get this. This is 2. When I multiply this by 2, I get 4. This is 4. So you see my 1 is walking. So that was 8 here. Now this is 16, 32 in binary, 64, 128. And then what happens? Well, what I'm going to get is that's the walking one. And see, this part here actually is going to be part of another group of 8 bits that is in front, right? If I start with 8 bit and I multiply that by 2, which is, let's assume is also 8 bit, I'm going to get 16 bits. So normally I would get a 1 that starts walking into the top 8 bits of the result. I know the result is going to be double the size of what I start with. So if A is 8 bits, then the result is 16. So what does Java do? Well, what Java does, the reason that I get to 0 is that it only keeps the lowest 8 bits, or in real, the lowest 32 bit. So when A is becoming very, very big, and I have a 1 in the most significant bit of the 32-bit storage, and I multiply that by 2, that 1 gets out and becomes the 33rd bit, which is part of the result. So inside the processor, the result is correct. But however, when Java takes the result and puts it back in A, which is an int of 32 bits, it only keeps the 32 lower bit, which are all 0. So that's why my program at some point loses information, and that walking 1 that has left the 32nd bit of my result ends up having 0 in A. So what does it mean? It means that Java, the compiler, if you tell it that you have an integer, which is what I have here, I said I want A to be an integer. So for Java it means it's a 32-bit value. If you're doing a multiplication like I have done here of A by 2, so I'm multiplying two 32-bit values together, because 2 is going to be coded as the integer 2 on 32 bits. So the result is going to be 64 bits. So the result of what I have highlighted here is 64 bits. However, I want to store it back in memory in A, which is the 32-bit storage. Java will keep only the 32 lowest bit and store that in A. And it will get rid of the top 32 bits, assuming they're going to be 0. But sometimes they're not 0. In that case, the result that you get is wrong. I have a wrong answer. However, my Java program didn't stop, didn't crash. I have no warning that this happened. Okay, so that's something that as programmers you need to know. So let's take a look again at that program that I have, and we're going to run it again. Okay, so you see 1, 2, 4, 8. So that's a walking 1. So all of these are powers of 2. So they have only 1, 1, and followed by zeros. And so that's why I picked that, sorry. All right, so the negative number, let's not worry about that right now. We'll worry about that later and figure out why the number is negative. But what I wanted to show you here is that A becomes 0 at some point. I'm losing that walking 1 that is still part of the 64 bits, but Java gets rid of the top 32, and so that walking 1, as soon as it enters in that area, gets lost. All right, so let's go back to where we were. Actually, I want to show you the other part of the program that I had prepared. So we're going to Emacs again. I don't need this anymore. I can get rid of it. Control K to get rid of that. So now I'm going to say if actually I can get rid of this part this way. Get rid of that. All right, so let's take a look at what I'm doing here. So this part doesn't exist. I have x, which is an integer, 32-bit. So just saying int makes sure that x is going to be stored in 32 bits. And I have this value in hexadecimal. So you see in Java I can write also 0x. And it has 1, 2, 3, 4, 5, 6, 7, 8 digits. So this is 32 2 bits in length, and it's a very large number. And this is the same value, and I'm going to multiply them together. Okay, so 0, 3 is quite large. So when I'm multiplying 0, 3 by 3, so when I'm multiplying really 32 bit by 32 bit, so the result is going to be a huge number. Actually, I have computed that. Let's see if I can find it again. So the number that I have in hex, if I translate that in decimal, that's the number that I would have here. If I multiply these two together, the result that I should be expecting is this long number with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 digits. A big number. That should be the result of multiplying this by that. But as you will have probably guessed, this is a 32-bit number multiplied by a 32-bit number. And when I'm going to multiply the two together, there's going to be a part that is going to be non-zero, some bits, into the upper 32-bit of the result. All right, so let's take a look at, oops, where am I? That. So let's run the program and see what it does. So I'm going to print x equals, so I can see the value of x in decimal. I'm going to print y equals, so I can see the value of y in decimal. Multiply x and y, put that in z, and then I'm going to display z. Okay, that's all that the program is doing. XC, yes. Java C again. Okay, now Java the program. All right. Look at the result. It should be 15 digits. That's 3, 6, 9, 10. It's 10. And 8 times 8 should be 64, 65, something like that. Let's go back here. Should be 64. The top two digits should be 64. So the top two digits are 16. This is obviously wrong. This is totally wrong. It's a wrong result. However, Java didn't say anything. It just computed it and truncated the result without telling us. We have to be aware of that. So as programmers, you have to be aware of that and know the size, how big your numbers are going to be, and maybe int is not what you want. So you may want a long. So you have Java supports a lot of different formats. Actually, we can very quickly. I haven't prepared that, but we can probably find that very quickly. Java data types. The 8 primitive data types. So yeah, let's take a look. Boolean, 1 bit. Byte, 8 bits. Char, 16 bits. That's for Unicode characters, which includes ASCII. Short, it's an integer that is 16 bits. So you see that Java actually supports words. What we call a word for Java is a short. And int is 32 bits. A long is 64 bits. So if you really wanted to play with large numbers, then long would probably be good. Otherwise, you have float for real numbers, 32 bits, and you have double, which are 64-bit real numbers. And here it gives you an idea of how the range of, or some ideas of how to write it. So if you want a long, for example, you can put an L at the end of the number in Java, and it will understand that you mean you want the number 2 coded as a long integer. All right. Let's go back here. So we've just looked at that. So how big is a 32-bit integer? It goes from as an unsigned. So again, I'm still talking about unsigned numbers that are only positive, start at 0. And so if you start at 0 and you have 32 bits, the largest number you can write, which has all ones, 32 ones, would be 4,294,967. Sorry, 4,294,967,295. 16 bits, you can go from 0 to 65,000. 8 bits, we've seen that 0 from before, is from 0 to 255. All right, so the div instruction works the opposite of MUL. So if you want to divide something, and so what is true with MUL is true with div. If you want to divide something by 32 bits, it better be 64 bits so that you can get a 32-bit quotient and remainder. So it's the integer division we're talking about. You don't get a real number using the div instruction. So you have to put in EDX and EAX a 64-bit value if you want to divide it by something that is 32 bits. And what you're going to get is going to be the remainder. See, the R here stands for remainder in EDX and the quotient in EAX. If you have an operand that is 16 bits only, you have to put what you're dividing by this operand into AX for the lower part and DX for the upper part. And the result will be the quotient will be in AX, the remainder will be in DX. And AX divided, if you want to divide by an 8-bit value, then you put the other operand as 8-bit in AX, which is a 16-bit register. And then the result you're going to get, the remainder will be in AH and the quotient in AL. All right. So I know it's confusing. I would recommend to read the documentation on div and MUL to better understand it. If you understand, don't try to understand both at the same time. Try to understand MUL, multiply, very well first, and then you'll see that div is the reverse operation. So if MUL is multiply 32 by 32 gives you 64, the div says you take 64, you divide it by 32, and you get a 32-bit remainder and a 32-bit quotient, because it's the integer division. And the remainder will always be in either EDX or DX or AH, and the quotient will always be in EAX or AX or AL, depending on the size of what you started with. All right. So we're going to do a little exercise. What I want to compute is this value here, 2 times alpha plus 3 times beta plus x minus 1, and I want to compute that in x. But now I'm really making it tricky on me because I'm assuming that alpha is a byte, beta is a word, and x is a double word. And in programs, sometimes you do have variables that are different lengths, because it could be that alpha comes from a sensor. Maybe it's an analog to digital converter and you're reading some samples from sound that you're sampling. In which case the number you're going to get may not be 32 bits, it may be 8 bits, maybe smaller. So sometimes you do have to compute things together that don't have the same length. So I'm going to show you how to take care of that, and it's pretty simple once you've done it once. So alpha is a byte, beta is a word, x is a double word, 32 bits, and they contain 3, 4, and 6 respectively. All right, so we're going to write a program to do that. I'm going to go here, quit this, Emacs, no window, demo, arithmetic, ASM. Okay, I'm going to show you a little trick. I'm going to include, now that I've opened a file that is blank, I'm going to include the skeleton. Control X, I, insert file, scale ASM, enter. All right, so now I have my skeleton. I'm going to write the name of the program, demo arithmetic ASM. All right, so that's what I want to compute. I want to compute x equals this. All right. Include files here. I don't need to include files. The data section, I need alpha, beta, and x. Okay, that's stuck here. So let's take this and copy paste here. All right. Looks better that way. All right, so now I'm ready to start. So add your code here. So the first thing that I'm going to do, I'm going to compute. So see, I need to compute 2 times alpha. So 2 2 times alpha. And because x is an int and it's a DD, I need to make everything that I'm computing a 32-bit value. However, alpha is a byte. So what I'm going to do is that I'm going to use EAX as my accumulator. I'm going to put 0 into it. So I'm clearing all 32 bits. Okay, and then I'm going to move in the lower part of EAX, which is AL, byte alpha. So I'm going to write as a comment that now EAX contains alpha. But the 32-bit version of alpha, which was actually a byte. So the trick was to clear the whole 32-bit register first, and then I can move into the lowest byte, alpha, and automatically the other bytes will not be changed. So EAX now is the 32-bit representation of alpha. And I need twice that. So add to EAX. So now EAX contains 2 times alpha. Good. Now, oops, I need 3 times beta. And beta is a word. I'm going to use the same trick, but I'm going to use EBX. I'm going to move 0 into it and move into, so BX now is the 16-bit version of EBX, so the 16 lower bits of EBX. Word, beta. So now EBX contains, I like to use the little arrow to indicate that EBX receives a value, which is beta, and I need 3 times that. So how am I going to do this? I want EAX to be 2 times alpha plus 3 times beta. So 2 times alpha. What I want to compute is 2 times alpha plus 3 times beta. So let's compute this, and if you see what I have, in EAX I have 2 times alpha, EBX I have beta. So if I add beta to if I add EBX to EAX 3 times, I should get 2 times alpha plus 3 times beta. Okay, so add EAX EBX. So now EAX will contain 2 times alpha, which it had already, plus beta, and my computer stopped responding for a while. Then add EAX EBX again. So now EAX contains 2 times alpha plus 2 times beta, and add EAX EBX. EAX gets 2 times alpha plus 3 times beta. Not bad. And now I need to add x and subtract 1. Okay, so let's verify that. Yeah, plus x plus 1. Oh, so x is already initialized. So I need to now compute 2 times alpha, which I have, plus 3 times beta, which I have in EAX, plus x plus 1. Well, add, since everything is in EAX, dword x to EAX. So now EAX contains 2 times alpha plus 3 times beta plus x. And I can use increment, which we've seen today. Increment EAX. EAX equals 2 times, 2 times alpha plus 3 times beta plus x plus 1. And now I need to put all this, Control K, Control Y, Control Y. I need to put all this into x. Move into dword x EAX, and that's it, and I'm done. That's my program. So if I run this, nothing will happen because I can't print integers yet, but you're going to see that very, very soon. Or you will have seen it, I think, by the time this video is released. All right. So let's save it and NASM it just to make sure that I didn't make any. Okay, so NASM doesn't crash or doesn't report any errors. No syntax error in what I've written. All right, let's go back here. So I'm done with that. And guess what? That's the end of that presentation. So that's the end of the video. Very good. I hope it makes sense. I know you're going to be having problems understanding multiply and divide read the documentation, try to understand it better, and hopefully you will be able to master it. Okay, we're done for this part of the lecture, and I'll see you very soon.